Good evening, everyone, to NFIC 2021. Prakash here on the AI for Edge services. So my background, I am a senior IEEE member and co-founder of Emerging Open Tech Foundation and have been the part of NFIC since 2016-17 and was the chair, program committee chair for NFIC 2018, which we had focused on smart cities and the edge. Here we are on 2021, and thanks to the partners, especially NATIA, the Taiwanese Association of North America, which has been instrumental working together with IEEE CS for several years, more than 20 years. And every year we come up with something or the other. And one change this year, welcome to the San Jose State University. We have been conducting mainly at Stanford, and last 2018 it was at the Santa Clara University, and this is time for San Jose University, and having a good time with the students here. So let me get to the substance. So my background is I have been in the edge computing for ever since 2013 when I met Professor Satya Mahadevan at CMU, who was my guru. He has been a great asset, and he started with the what we call as the cloudlet, and as part of the OpenStack, and then later participated to ensure that we do have participation. And there is one company, Inspur, which is part of the Taiwanese companies in the OpenStack area. They were part of this, and they also contributed to the Edge cloudlet called as OpenStack ++ during 2016-17 timeframe. Now the changes have occurred, and last 10 years I have been talking about a lot of things in the Edge. We have moved on to AI, and so AI for Edge is the service which is taking off in a big way. And so today our focus will be on the AI for Edge services. So how to accelerate, which is a part of the topic, and offloading and acceleration are the two key processes, or two acts which the solutions and the products provide to the edge, and we'll be going through those as part of our management control, data plane, and whatnots of this cloud and edge ecosystem. So let me move on to the first, why edge computing. So edge computing, do you really need, or can a cloud alone do it? If cloud alone were doing it, then the where the user is. So you have the user edge and you have the cloud edge. So cloud edge is more a network edge, and which you see on the right hand side here with a non-optimal way of delivering a service which is high latency, 25 to 200 millisecond, which is not desirable for a low latency requirement of application, which is in the 20 millisecond or less range. And you can see the examples of them are there. If you have NFV, network function virtualization, could be a load balancer, could be a firewall. Those are the middleware functions, and if there is any edge infrastructure that needs to provide, then the latency and devices example is UV. There you know that you have been using drones and unattended vehicles, UAVs. So drone and UAVs with camera loaded, trying to capture the information in the field, whether it's an arena or a field. Obviously, the latency requirements and computational process requirements to process the stream is very important to be on the lower side of the 20 millisecond. Therefore, you find that is one interesting area where you need edge computing. Same with immersive experience. If you have a Google glasses, or even for that matter, you use Oculus what do you call the devices, you wear them to that's another use case. And then you have industrial IoT, which is the Internet of Things, and in the industrial sense, it is in the factories and warehouses. Again, require a fast, low latency and high throughput processing and closer to the location where the application is being used. So thus we see that edge computing is here to stay. It is going to be there, and there is a requirement for it. And once there are commercial use cases and application, obviously there are players to take advantage of it. And there are different models, so we have to consider. Let's start with the models. What kind of models do we have for cloud and edge management? So looking at model 1 here, you have a cloud controller managing an edge controller, one or more edge controller, and each of these edge controller manage the nodes, and the nodes within them have either a pod or it could be a container with an application on that. It could be a VM. So what it means is that any application can be packaged as a container, and within the container, and can be managed by the edge locally, but they can also be managed and controlled. Managed and controlled. You can see in the diagram mode 1, edge 2 is being managed, not controlled, whereas edge 1 is being managed and controlled, and with the data and the applications running in the nodes, and the data between the nodes being shared. So this is one kind of a cloud controlled edge. There are images that can be used locally or can be obtained from the cloud controller. So this is one model of. The other one is a standalone edge where it self-controls everything right from the images to instantiation to the node, both the data and the application. So management and control resides in the edge 3, whereas the nodes themselves have the data application and data sharing across the nodes. Then comes one of the popular models, Model 3, which is the Iot Edge, where you got a gateway as a controller, IoT gateway acts as a controller. It could be a home gateway, it could be a third-party gateway, like your Fitbits or something, where you're exercising and getting your sensors strapped to your body and being measured and uploading the data into the gateway. So that is your management, control, as well as application being running and data being transferred between the sensors and the gateway. So that's one of the IoT Edge use cases on models 3. Then you got fourth model here where you got edge controlling the edge. So you have one edge being the master, the other being the controlled. So you got the management, control, and data floating between them, and the applications running in the nodes, which are under different edge locations, and they all contribute to the data, and data is being shared across. That's another model. Then you got the fifth model where peer-to-peer. So both edge can, neither edge controls each other, but neither is a master, but each of them independent. But they do, neither of them is a, yeah. So by management and control of perspective, they take care of their own nodes, whereas the peer-to-peer is only a matter of data sharing. So that's model 5. Then you see model 6, which is at the bottom, as you can see here. You got 4G edge controller. Here it is more like a MEC pattern. MEC is a mobile edge computer. Or it's turned out later on, it's called multi-access edge services. So this is a MEC model where you have the vBBU and the virtual BBUs are pulled together, and you got the evolved packet core, the 4G evolved packet core, which is at the back end. So you got the S1 interface for the user where you got the data flowing, and you can see this is one of those micro data centers where you bring the local breakout for the application to be served to the consumer for the mobile, and for even, for that matter, even fixed. So this is one of the 4G local breakouts. It's a bump in the wire type of arrangement. So last but not the least, the seventh one. This is all INGR IEEE has defined, seventh, which is the 5G data router, which is data router is connecting. If it is at the cloud, then it deals with the backend and the user plane function in the next generation user plane function. And if it is a MEC with a 5G combined, then you have an edge user plane function, which is nothing but a breakout, but not called breakout, it is called as a data routing or at the edge user plane function. So let's get into more detail here. As we see here, next we have got the edge deployment model. So IEEE INGR Edge, this is the model 7 we discussed, and this is the one which provides the function as a service. Example, you can provide a acceleration function or a offloading function at the MDC or micro data center. It started as a nimble few kind of a one or two server to tens of servers, and ultimately it has come to something like now tens of racks of servers. Each rack can hold around, let's say, 14, 16 servers, one U or 2U combination thereof with a 42U rack. So you can see that the approximately you can say hundreds to 200 servers is the limit. Generally 150 is more likely in a normal edge data center, micro data center, I would put it. But this is moving towards many, as you may, hundreds of racks, 50 to 100 racks, which is becoming required because of the density of the application being run at the edge. So they are time sensitive, they need to be real time, they have to have a low latency, they have to have high throughput, They are compute intensive and they need to be intelligent. So those are the factors which make the edge deployment for the 5G data routing and the edge user plane function a little bit more complex and dense. Now, this is our another standard. Of course, there are many standards, and HC has got another similar to what we have in INGR, as we described the nodes, the Kubernetes nodes based, container based deployment of the edge. 1M2M is nothing but a IoT standard from HC, and they have a three-layer application layer, the common service layer, and the network service layer. These three being the entities representing application entity, common service entity, and network service entity. Now, these have interfaces, and they can be combined. Some places it can be only, they can be either dedicated application entities, or they can be combined with common services, middleware services, and generally those are the two combination. And network services generally are managed independent because they are managed by the network provider. So getting into details of who owns and who drives, you can see here on the right side there are three main actors. One is the operator application service provider, whose focus is on the M2M application development. So they are more development centric, providing tools for development to the end user and to the developers. Whereas the middle layer, which is so the top layer, application layer, has flexible containers being available, flex containers as they call it, which can be developed and they can have the images and people can use the images of specific application. So it's like a packaging ready-made and try to speed up the operation so that onboarding is easier and people can use it flexibly, and then they can replace or update as things change. So those are the gains of containerization which can be exploited by the flex containers. Then you got the common service functions, which are like very simple: registration, deregistration, discovering the application, data management in the repository, and group management and subscription notification. All these supported mechanisms are available as part of the middleware in the common services function. So that's one way of looking at a edge service as being a IoT service or M2M service. And obviously the underlay we want to separate out because a network is complex and better to manage the network, especially if it is a existing network. You just need to apply overlay. So the fundamentally the underlay and overlay are separated out, thereby the focus of the providers is in different area and they can charge for that. And this is a collaborative effort for implementing the edge, or one, in this case it is a 1-to-M edge. So there are different solutions to that, and you can see here a 1M2M HC a general purpose IoT framework they have described here. And this shows that your application 1 and 2 and 3 using the same common service. So the application entities use a common service layer, and that common service layer can be from different providers or same providers. At the same time, you can have a gateway, which is the gateway edge gateway for processing node, and they can have their local things in the local network with devices and sensors and all those inputs in the local network. You can also describe them as edge spaces. So you can have different spaces, and these spaces communicate with each other through the networks provided by network provider A and B, and they can all be talking to the common layer, which is services where application entities can provide the application services through the common layer. So here the picture is that you have things or devices and sensors that are spread across the edge spaces, and those are in their local networks, and they can choose to use the networks which they can optimize and produce the uh, viability of cost and value, and then use accordingly. So this is one of the frameworks which is also popular. So normally all frameworks lead to some kind of a software, and the software is what it allows you to interface different ways using different uh, standards, yet they tend to work together. So from the IEEE INGR, where I come from, we are looking at the edge service as an endpoint, and we also look at cloud service as an endpoint. The only difference is that edge service is closer to the user, and you can see that uh, the developer and app and the devices which the user use, they have to be first uh, validated, that is authorized, AAA function, that is authorization, authentication, and then making sure that they have the access. So those are the three which is in the control plane. So if a user connects to edge service, they can access through an endpoint. That endpoint can then connect to the service. If it is local, it is local. If it is a distance larger than say 300 kilometers, then it's a problem, because you lose 1 millisecond just for the forward. If you take 300 kilometer and 3 into 10 raised to 8 meter per second is this speed of light, at that speed you can still, you will consume at least 1 millisecond one way. Two way will be 2 milliseconds. So you are already 2 milliseconds away in the round trip. So better to have edge service closer so that you can get sub-millisecond response time with communication. Then there is another element of compute which is over and above it. So edge service endpoint can define the endpoint, then you can register, deregister, you can stream, you can do whatever the API supports. And same thing can be done with the cloud, but onboarding is different there. Here the onboarding is different. Most of the time you would prefer to do it on a container, whereas endpoint where the cloud services, that it may be on a physical bare metal, sometimes even in virtual machines. And so if you look at the node N0, N1, N2 at the bottom with the service, what does that tell? That you can have Kubernetes nodes and clusters, and you can work connecting them together, all the resources that are there in the edge space, and they can be providing the service as composition of services based on different node, different pods, doing different functions. Some pod can be a security pod, service pod, some can be a, what do you call, sidecars, which can provide additional policy management, etc. And then you can run the app. The app can be then sourced by the user through the tunneling, which they can establish as a virtual private cloud into the edge, or virtual private edge cloud you can call it, and connect them and signal the data, and then use that. So this is how a normal control plane and data plane functions are nothing but sharing the data either through network or kilometer is normal, and that gives you a 10 millisecond one way trip. Two way it will give you around 20 milliseconds. So clouds, generally we do not expect with LTE and 4G anything better than 20 millisecond response time from cloud. Even with 5G, still the response time will be lower, even if it is, because 5G only covers the radio portion of it or the over the air. But then beyond the over the air, then your connectivity is all physical, which is the standard underlay, which is MPLS or maybe L2, and then it can be over the media. It could be fiber, or it could be copper, or it could be some of those underground undersea cables and all that. So that's why we don't get into that. That's a longer distance, and usually for getting low latencies, you should be able to run your application at the edge. Edge can be user edge, which is more to closer to device, or it could be at the network edge. In either case, we are seeing that our point of view is based on edge service endpoint, which is a URL and which is describing and which can be connected through the API, and you can execute the application within the nodes or in the containers, in the clusters, in the Kubernetes cluster at the edge. So we have done the part of edge now. We are already 20 minutes into the process. Let's talk on the AI now. So AI is obviously it is the artificial intelligence, and you can talk of intelligence. It's artificial because it is not human intelligence, it is machine intelligence or device intelligence. So the intelligence which is there, which is artificial and which is embedded in the devices, and that can be capitalized on by the applications. And so some of the examples are NFP Edge infrastructure, NFP Edge infrastructure here. This is showing VRAN and the VEPCs. These are nothing but the 4G RAN, radio access network, cell towers, and the EPC is the back end, which is nothing but you got packet core. So packet processing, the packet gateway and the serving gateways type of things. And this can be accessed through wireless. Of course, your mobile device, Androids and the iPhones of this world smartphones can access them. And that provides you the application. Now, autonomous devices, so UAVs and drones, as we spoke earlier, that is unattended vehicles or drones. They can do with the camera, they can do a lot of applications, whether it's agriculture field, figuring out what the soil content is, or those kinds of applications, or it could be some of the security applications. Virtual reality, we already spoke about it. Again, that is another is required rather for them. Now, whereas for the Open RAN APIs and all that, they require real time. That may be very sub-millisecond and very difficult to build. But on the other side, you've got augmented reality, home devices, and autonomous vehicles to be able to, like, steering the car and in the middle of the road, not steer while there is one with the driver with the driver being in the car. Driverless is without the driver. Autonomously the vehicle will take the pictures across through lidar and radars and process it and then drive the vehicle. AV autonomous vehicles at the level 5 is when they do automatically everything. At level 4, still there may be a car driver sitting, but not really driving, but cruise control. Then you got other SD-WAN application like UCP and all those. Those are devices, that is the customer premise equipment, and they can be used by the enterprises for the SD-WAN. There is software defined wireless area network. Then you got the industry robotics. Robots are there which are used for by various like hotels and some of the services when you see them at the edges. So some of these are very popular here in the Bay Area, at least in the schools and all. A lot of schools do compete for the robots based applications. Then you got the video, 360 video. You can see a panoramic view of all around. Retail, for retail you use for the whatever the comparison, and for what you call the ability to cross sell and all that, and depending on the user perception and user behaviors and what they look for often and all those. So those are microservices. Then you got the IP enterprise services which deal with the IP requirement at your enterprise, like you might be doing a video conferencing, audio conferencing, those kinds of application. Then you got medical, where you do the applications like telehealth. Then these are the wearable cognitive assistants which you use normally, Fitbits type of devices and all. And then you got healthcare, where emergency healthcare management is done through 911 and all those when you call. So these are some of the AI applications which at the edge which AI can be used and leveraged, and this is part of the edge computing. So we have got edge services, plenty of them in different domains, all being driven, requiring AI and kind of intelligence which you can provide artificially. And a little bit of text. This is all you saw in icons. Now, some of the applications which are like AR, VR simulations, those are like you do 3D rendering and all, which you must be using your GPUs and all that, neural network, and they can use mixed precision. So those are some of the areas where, depending on cloud to edge you will be using lower precision, get the optimization to the best. So there is another thing which is known as universal scene descriptor from Apple, which is being used extensively by NVIDIA as well as by the Adobe. They can provide you the scenario, so you can describe your game, or you can describe your design, how you want the scene to look like your architectural view of your Twin Tower example, which was conceived, and then you can build it, deploy it. You don't have to build and deploy physically, but you so you can do the image object recognitions, and then you can do similarly something like trying to figure out a cat is a cat or an object is a trying to inspect or detect a particular based on the libraries that are already available. And this can also be used for inspections of, for example, a aircraft, and if you want to identify the part replacements and all that, that can be done using the multimedia. So helps, this is like a help, but self-help. Then logistic is for moving and all that. You can move a lot of goods from the, what do you call, the shipping terminals and to the manufacturing and all that. So those kinds of applications. Inferencing, training and inferencing are main for the AI ML model. So when you build a model, then you need to have some samples and identify how you fit the curve, whether it's a convex, concave, or whether it is a nonlinear function, whatever the linear or nonlinear function that you try to curve fit. And those kinds of are like a recommendation systems, uses them. Then you have encoder and decoder which use them. So encoder decoder could be for the media, it could be for audio, video, codec, those kinds of which require a lot of calculations. Then you got streaming video. Of course, you can live monitor and control and stream, and this requires just-in-time delivery. Could be for supply chain or it could be for training. Then you got streaming audio. Audio is again voice activated application. You can have ASR is nothing but automatic speech recognition. You can have speech to text, text to speech. NLP, that is the natural language programming for conversation. You can have talk in English, convert in Mandarin, or talk in Mandarin and get in. So you can do language translations, etc., etc. there. Then you got AVS, which we already covered. Steering and braking. It could be also V2I, V2V. There is vehicle to infrastructure, in the intelligent transportation systems. These are very popular. And then you got it could be ad hoc, like platooning type of application. When you run V2V, a military truck is running and another military truck is following, and they are the only people, so they have to use ad hoc network to trace each other while they try to work in remote, in the darkness, etc. That's one type of application. Then fintech, you got transaction, you have ATM, blockchain. ATM is your automatic teller machine. Now you can withdraw funds from there. So at the edge you will have the front end, at the edge you will have the ATMs. All the behind the scene work will be taken care by the back end banking or processing. You can also use blockchain for the crypto and asset tracking and all this. Emergency management usually requires alerts and for floods and for earthquakes and for many emergency situations, riots and all that. And this usually can be done through messaging, whether you use a MQTT or whether you use a pharma manufacturing, drug formulation, like all the process control that goes behind it, whether it's a PID control or whatever controls you have in the manufacturing, plus the packaging and delivery of the medical tablets and all that. Those are some of the manufacturing applications of machine to machine or IoT, industrial IoT or IoT 4.0, what we call. And in this pandemic era, we had a contact tracing application, mobile application, as well as the contact backend. Mobile application runs just to give the information and then providing information that is relevant to you, as what are the nearby patients who might be impacting you and how to avoid a particular area, types of things. And offline alerting and tracing. So you can do offline tracing once you reach your place, you can submit. So there is no writing. It's just to maintain the privacy. Only you get what you need to know basis. Those are the kinds of applications. So this gives a coverage on again deployment of different in a little bit more deeper way. Let's come to now what is the industry doing for the APIs to enable the AI workloads at the edge. So you do have one standard evolving from the Intel camp called OneAPI. They have the intelligence it has, and usually it's more of a discovery process as base driver, whether the CPU is there, GPU is there. CPU is the only one which is host. The rest of them are called devices. So you have a GPU device, FPGA device, or other any acceleration devices. So zero level API is the one which is the baseline. Then you got the DPC plus parallel computing, because you have to do what you call the kernel. They call it kernel here for running a device, a process in the device. So the thread that initiates will be the CPU thread, and then pass on the control to the GPU thread, which in turn will GPU kernel, which in turn will use the parallel processing to compute, and therefore you have DPC++, which is the standard C++ with some variations and some additions to be able to support the MPI, OneAPI, OneCL, and there are many libraries or standards used by different processors and process lines coming from AMD, from Intel, from NVIDIA, from MIPS and various other manufacturers. So architecturally they are different, but they try to come together under Chronos. There is something called Chronos standards, and that standard it's a binary standard based on certain header and some kinds of instructions, and those instructions variable length they can be, and it's a opcode and operands specification which goes into the ISA, so they can be used as single instruction, single data, and multi SMID, and it's a single. So you have got instructions. So various, you can have a single instruction, a single data stream, or you can have a single instruction, multi data stream. So usually SIMD is the one which is used for the parallel processing. So you can use SIMD. So that's what it is. So you got various collections here. Communication library, which is for the shared memory and for the various transfers between the serialization, deserialization, those kinds of things. Then you got the data analysis library, which is dealing with the data analytics for the big data, for the Hadoop, for the streaming data, and those kinds of things. Then you got the deep neural network, which is library for the DNN, CNN, and all that. Then is distributed neural network. Neural network is nothing but neurons. The brain should take one dot or one neuron, and that neuron is connected to another neuron, and then there is a layers of neurons. So it's a basically input layer, output layer, and hidden layers. So you map whatever you see. It's a weight. It's a simple multiply, add, and accumulate, which is what you do in a filter. Digital signal processing, you can do FFT, DFT, all kinds of FTs. So those are the ones which are based on the neural network library, and it includes those examples of them are PyTorch and what do you call these are the various libraries available for neural networking. Then you got the math library, math and kernel library, which is nothing but your these are the ones which are related to the scikit and NumPy and those kinds of things which you already know, and you can add to that additional tensor processing and all that, and matrix processing, tensor processing, all that. Then you got the threading block, which is the normal threading that is for the MPI, message passing interface, and all that, so that you can process based on the rankings and all, which is associated with the MPI. Then you got the ray tracing, which is more to do with the what you call the image visualization. And when you visualize image, if a line is moving, and if you have a water in, then the reflection of the line comes, so that should be visible, kind of thing. Those are the kinds of ray tracing, how the darkness or the lighting in a particular view, how it appears, those things. So ray tracing is very popular, and it's not just available here, it is available in all the places. So let's move on to the competitor, which is also NVIDIA. It has got a offering called DPU, and that is becoming very popular because it is a kind of a smart NIC. It's a network interface card type of thing, which has a SOC, and which is able to provide on ARM instead of x86 architecture. You can run your VM and container on top of DPU. Which has got the infrastructure management, software-defined storage, software-defined security, as well as the SDN software-defined. All these are accelerated